Okay, so we've got two categorical variables, and we want to know, are those variables independent? Now, you've probably heard about independence before in some of your other math classes, probably when you're talking about something like probability. And you hear that word independence as in independent events. Normally, we think that independent events are ones where the first event doesn't affect the probability of the second event. So, for example, if you're flipping a coin multiple times, those are independent events because every time you flip the coin, you have a exactly 50% chance of getting heads. You don't flip the coin 3 or 4 times and it goes, oh no, I've been heads the last 3 times. I better be tails this next time. So you're not more likely to get tails if you haven't gotten it for a while. Okay. Similarly, we could have events that are independent with like cards. So I draw a card out of a deck of cards, and there's a 50% chance, 26 out of 52 chance of getting a red card. So if I put that card back in the deck and draw a second card, I still have a 50%, 26 out of 52 chance of getting a red card the second time. Those would be independent events. If I'm talking about taking a card out and I don't put it back, and then I say, so that there's a 50% chance that that card is red, and then I say I'm going to draw a second card, what's the probability of that being red? Well, it depends. It's not 50% anymore because now there's only 51 cards in the deck. It depends on what I got the first time. If I got a heart or a diamond or some red card during my first draw, that second probability is now 25 out of 51. But it depends, because if I got a black card that first time, like a spade or a club, then the second time my probability is going to be 26 out of 51. Neither one of those is 50%, even though they're very close. So the idea of that probability, that second thing changing because of what happened the first time, or in other words, you can't answer that second question without really knowing something about the first question. That's kind of how probability and independence works. So when we're talking about variables, the idea of independence, for the most part in this chapter, all we're basically looking at is by inspection, do we think that there's some sort of relationship between these two variables? Do they seem to have some sort of relationship? Are they associated with each other, or are they independent? One variable doesn't seem to have anything to do with the other. One question you can kind of ask yourself is, are you more likely to be some category of variable 1 if we know you're some category of variable 2? Now, there's a couple ways to look at this. The one is a computational method. So we're going to look at the conditional distributions. If your conditional distributions, remember, a conditional distribution is when you look at a subgroup as 100% and show how the categories are split up within that 100%. If those are the same, it might look like this. I have two variables here. I have a variable of political party, and I have a variable of area of residence. Excuse me. So political party and area of residence. And for political party, you could answer Republican, Democrat, or Independent. And for residence, you could live in a rural, suburban, or urban community. And we did a little survey and recorded the data in this contingency table. Now, if you'll notice the conditional distribution, or the one that adds up to 100% here, 38, 35, and 27 add up to 100%. But it's also the same, 38, 35, and 27, in each of the other areas of residence. So if I asked you, let's say we're just looking at Republicans, for example, and I said, what percentage of our sample was Republicans? Well, you can answer 38%, and you don't need to know where the person lives in order to answer that question. So I don't need that other piece of information. So it's probable that the variables are not associated in this case, that there's no relationship between them, and therefore they are independent. Okay, so my variables, political party and residence, in this case, they look like they're independent. It looks like I can answer questions about political party without having to know where you live, because it would be the same. It doesn't matter. It doesn't depend on that. The conditional distributions, if they are not the same, so for example, for the rural communities, I've got 38, 35, and 27 again, but then I've got 28, 28, and 44, and 40, 45, and 15. Okay, those are not the same. They all add up to 100%, but the distributions, excuse me, the conditional distributions are not the same. So again, if I look back at Republicans here and I say, well, what percentage of my sample or what percentage of my population were Republicans? And I said, what is that? You would have to say, well, Mrs. Leahy, it depends. Do you mean rural Republicans, suburban Republicans, urban Republicans? You have to know this other piece of information in order to know what answer to give me. So the distribution for all the categories, the distribution about how 100% is split up amongst those categories, for it to be independent, each one of those has to be the same distribution. Okay, you don't have to have the same percentage of Republicans, Democrats, and Independents, but the Republicans needs to be the same for all subcategories of residents, and the Democrats need to be the same for all subcategories of residents, etc. Okay, now this is really easy to see with our segmented bar chart, not as much with our comparative bar chart, but if you have a segmented bar chart, then what you can do is you can kind of look across the x-axis and within that category here. So what you're going to see is if the two variables are independent, then your segmented bar charts are all going to look the same. And if you were to look at, say, the percent Republican all the way across, that's going to be equal. And the percent of Democrat all the way across is going to be equal. And the percent of Independent all the way across is going to be equal. It's almost like you have the same segmented bar chart. Even though your raw numbers might be different, the proportions are how those are split across. So I could answer the question if you said, well, what percentage were Republicans? Well, it's the same no matter what. It looks like it's about 38% in this picture. If the variables are dependent, then, or associated, sometimes we use that word associated. Okay, if we've got some association or it seems to be related in some way, then what you're going to see by inspection is a different distribution of variables. So the percentage of Republicans or Democrats or Independent, it just takes basically one category to mess this up, okay, is not the same as you look across. So we would look at this and say, oh, these variables appear to have some association. These are not independent because the percentage of rural Republicans is larger than the percentage of suburban or urban Republicans. The distribution of political party is not the same across those subcategories of residents. Okay, a little bit of a film cut here because I dropped my stylus and it rolled across the room. So to cut back where we were, if you were asked to talk about this, then you would want to make a basic statistical argument here. Here's what the generic argument would look like. Something like this. You would say like if, let's see, I'm going to type here instead of writing this out so you'll be more likely to read it. Okay, so I'm going to say if whatever variable 1 is, variable 1, political party, whatever, if variable 1 and variable 2, and you would put those in context, you'd use real words, are independent, we would expect that the distribution of variable 1, which I can't seem to write, variable 1 would be the same for each variable 2. Okay, then the next thing you would do is you would basically explain what you see with real numbers. And then finally, you would answer the question, or you would make a decision about what you think is true about independence or association. So let me come up here really quick and see if I can bring that back up to this. All right. One more. Okay, so let's say I was looking at this picture. So I would phrase this and I would say if area of residence and political party are independent, we would expect the distribution of political party, because that's the one that's being split into 100% here, the distribution of political party to be the same for each area of residence. Okay, what do I see? It appears that the distribution of political party is not the same for each area of residence. For example, the percentage of Republicans in the rural area is 60%, which is larger than the percent in suburban, 50%, or urban areas of 20%. Also, the percent of Democrats in the rural area, about 12%, is much smaller than percent of Democrats in the urban area, about 15%, or urban area, 10, 20, 30, 38%. Okay, so we continue to give examples. So I'd say if they were independent, I would expect the distributions to be the same. Distributions are not the same. And I would give examples of how they're not the same to show how one category is different across all three bars. And then I come to my decision. So political party and area of residence are not independent. They appear to be associated. Now, if I was having that same argument up here in the first picture, I would say if political party and residence were independent, we would expect the distribution of political party to be the same across all categories of residence. It does appear to be the same with Republicans approximately 38%, Democrats about 28%, etc. And I would give those percentages for each category for each area of residence. So it appears that political party and residence are independent. So that's the argument that we want to make here. All right, so I have this little picture and it says, the chart shows the proportion of personal computing devices sales globally in 2008, 2012, and 2016 by operating system. And I'm not sure why, but the word year floated up here on the relative frequency bar, and it really should go down here. So if you're taking notes along with me, you should put year down there instead. So I have two variables. The first is year, and the second is operating system, Microsoft, Apple, or other in this case. And we've got relative frequency over here on this axis. So do we think that these variables are independent, or do we believe there's some association between them? So the first thing I would do is I would go to make this statement, and I would ask myself, what do I think is actually happening here? So let's see. If operating system and year were independent, we would expect the distribution of, and what's being distributed? Where's my 100%? Let's see, that's going to be operating system there. The distribution of operating system to be the same each year. Okay, now you don't really want to say it if you can help it, because that's very non-specific. So the distributions are not the same. For example, the distributions are not the same. For example, in 2008, that's that first year, the percent or the proportion of Apple was 0.06, which increased to 0.2 in 2012 and to 0.25 in 2016. Okay, also Microsoft decreased from 0.66 in 2008 to 0.3 in 2012 and 2016. Okay. Also, what's happening with the other brands seem to fluctuate year to year, with 0.28 in 2008 being the smallest, and 0.45 or 0.50 in 2012 being the largest proportions. Okay. Okay, so because that's what I'm seeing, it's different. It's definitely different. Here's how they're different and changing those percentages there. So it looks like, it appears that operating system and year are associated. They are not independent. Now, somebody in one of my other classes said, Mrs. Leahy, when I look at this graph, one thing I have a question about is, what if this first bar wasn't there? What if you only had these second two bars? What if that's the only part you could see? How would you answer that question? Because they're not the same, but they're really close. All right, so in this case, if you're looking at a problem like this, one thing I want you to hold in your heart of hearts is that we are going to actually later on in the year do something called a chi-squared test, where we're going to be able to calculate the probability of getting results like these if the variables are independent, and be able to test to see mathematically if we think that this is different enough for us to say they're associated, or if it's not different enough. But for right now, you could probably argue this either way. Technically, they are not the same across there with 20 and 25% and 50 and 45%. But you might be able to make a pretty valid argument, something that along the neighborhood of, if operating system and year are independent, we would expect the distributions of operating system to be the same across each year. The distributions are very similar, with Microsoft at 30%, Apple at 20, approximately equal to 25%, and other at 50%, approximately equal to 45%. Like I would literally write on my paper like 0.5 is approximately equal to 0.45 there. In 2012 and 2016. Therefore, it's plausible that operating system and year are independent in this case. So a lot of times too to kind of think about is, are we taking a sample or do we have a population? If it is in fact a sample, remember that we don't have all of the data, so it could look slightly different in the actual population. Okay, one other thing that kind of pops up with these, there is an issue with always using percentages instead of raw numbers, and then we do lose a little bit of information. So I have a graph here, and here's our lovely segmented bar chart. Here's a comparative bar chart, and this problem says Yellowstone National Park surveyed a random sample of 1,526 winter visitors to the park, and they asked each person whether he or she belonged to the environmental club like the Sierra Club. Respondents were also asked whether they owned, rented, or had never used a snowmobile. So I have this contingency table over here. And, you know, we have this data, we've got this, we're looking at this. These are beautiful graphs. They use relative frequency. What my eye is naturally drawn to, however, is this blue bar. Look how wow, 70% of the people who said yes have never used a snowmobile. That's a really big percentage of the data. But it's what aspect is missing of these? So the thing that we lose is we actually lose those raw numbers. We lose those frequencies. So a piece of information that drops out of this is, even though this is the very largest section in area, it's only 212 people. So, and this little green area up here, that is the owned and the no, that's 279. Okay, so even though this is a huge area, it's actually far less than the very smallest area on the other graph. Okay, so the areas don't really match up with the frequencies. But we keep saying, well, Mrs. Lay, why do we care? You keep saying relative frequency is better if the sample size is not the same. Okay, so I like to think about it in terms of Amazon reviews. When I go to buy something on Amazon, I always look at the reviews. And if something has a 5-star review, I'm like, wow, that looks really great. But if there's only 3 reviews, you know, we got 3 reviews on that, I'm not nearly as impressed by a 5-star review that has to do with 3 as much as I'm interested in a 4.5-star review where 10,000 people have answered that. So the one thing that we do lose is how many. And if you look up here, if you were to look at the marginal distribution, this 1221 is 80%. And this 305, that is 20% of the total. So there's almost 5 times as many people, sorry, 5 times. There's 4 times as many people who said no than there are people who said yes in this case. All right. So how can we fix that then? So if we really want to fix that, one of the things we can do is make something called a Mosaic Plot. Now, this is basically a segmented bar chart that still allows us to see on that vertical axis, vertically, when we look at these, we can still see that conditional distribution, okay, of snowmobile use. We can still see how snowmobile use here. We can still see that conditional distribution. I can still tell that about 70% of the people who answered yes have never used a snowmobile, and that about 22% of the people who said no have owned a snow. I can still see those percentages up and down. It's still a segmented bar chart. If I was just to look, there, it's still pretty much what I had on that previous page. But the other thing that shows up is on this horizontal axis, what you have is the marginal distribution of your other variable. Okay, so what you're able to see is that 80% said no and that 20% said yes, because literally the area here is 4 times as wide. And what we're able to see is we can actually keep an eyeball on our frequencies now. I can tell simply by geometric area that the fewest people are up here in the corner in green, and that the largest number of people were here in the no and rent section. Okay, so it kind of adjusts for that. I can still see that. I highly doubt that you're going to be asked to make a mosaic plot on the AP exam, but if you did, it would be really easy to do. Figure out your marginal distribution, sketch over a horizontal axis, and mark off 10 spaces that are equally spaced, and then measure your 80%, 20% by like 8 out of the 10 spaces and 20 out of the 10 spaces in that case. Okay, so you can adjust that height there. All right, so let's look at this last question. It says for body image, a random sample of 1,200 U.S. college students said, what's your perception of your own body? Do you feel that you're overweight, underweight, or about right? And we have the two-way table summarizes this perceived body image by gender. All right, so of the respondents who felt that their body weight was about right, what proportion were female? So again, of the respondents who felt their body weight was about right, we're not talking about the 1,200 here. We're only talking about the respondents who felt like their body weight was about right. So I'm only talking about this 855, and it looks like 560 of those are female. Okay. Notice this says what proportion. In general, when you're asked for a proportion, we're usually going to leave that as a decimal between 0 and 1. A proportion, usually looking for that 0.655 here. All right. Now the next question says, let's see if I switch my little highlighter color here. All right, next question says, of the female respondents, notice, so not out of everybody, just out of the female respondents this time, what percent felt their body weight was about right? So it's still 560, but this time we're talking about the condition that the person is definitely female. That's 760. So 560 out of 760, that gives me 0.737. And notice it says what percent, so I'm going to answer it like that, 73.7%, as opposed to the proportion of 0.655. Okay, the next question says the Mosaic plot displays the distribution of perceived body image by gender. So in other words, we're looking at the percentage of females and the percentage of males. So this 73.7, that's this section right here. Similarly, if you were to compare this for males, this would be the 295, about right, out of the 440. 295 out of 440 gives me about 0.67 or about 67%. So the question says, describe what this graph reveals about the association between these two variables. All right, so I'm going to start off, and I'm going to say this the same way that we've been saying it. If, what are my variables? Gender and body image. If gender and body image are independent, we would expect the distribution to be the same across both genders. All right, so I'm going to say like if the distribution, if gender and body image are independent, we would expect the distribution of body image to be the same across both genders. Okay, it is not. Oh, I said it. The distribution is not the same. For example, the percent of females who said about right, which is 73.7%, is larger than the percent of males, 67%. Okay. I would also, and just for sake of time, I'm not going to type this in, and for space, I would probably talk about those other categories as well. So I would put in some other examples here. I'd go ahead and say something like the percent of females who said underweight is very similar to the proportion of males, but the percentage of females who said underweight was significantly smaller at about 5% to the percentage of males who said underweight if we're looking at the green. So the green kind of compare how that is different as well. Okay, therefore, so it appears there is an association between body image and gender. All right, so if body image and gender were independent, we would expect the distribution to be the same across both genders. Here's what we expect to see. Here's what we actually see. Here are our examples that show that what we expected to see is not what we got. So therefore, we believe that there's an association between these two. All right, so good luck talking about independence and examining mosaic plots.